Good day. All right, here we go. So we're talking today about more about simplifying roots. Okay, so you got some basics down for them, and some of the lessons today will be reviewing some of the basics you already know. Then it goes a little bit crazier too. And what if you divide roots? And what if you have to add, subtract roots? And how do you rationalize denominators, which is something that we'll talk about later on. So it's a heavy day. So I do need you to kind of pay attention. And we're going to do a lot of notes. But let's review the basics before we go on, because it's what we just did, graphing things. Okay. So looking at these equations, we should be able to spot a few things about them. Number one, it's an even root. So right off the bat, it looks kind of like that, correct? That's what even roots look like. You should also be scanning for negative signs involving reflections and things, because we need to know the shape of this thing. So I see a negative in front of the root. If it's in front of your function, what's that do? That's a vertical reflection, right? We've done that like 80 times all semester long. And if there's a negative in front of your x, it's a horizontal reflection. So I see two reflections. Now, what would happen if I reflect this vertically and horizontally? Well, vertically, it opened down then. Would you kind of agree it looked like this? And if I reflect that horizontally, this would now look like that. So in my mind's eye, I'm thinking it looks kind of like that-ish. Okay, I got the reflections done. I know the basic shape. The only question is, where the heck do I put the vertex? Well, that's when you look for when the stuff under the root is 0. And if you set that equal to 0 really quickly, if you move the 2x over and divide by 2, that happens when x is 2. So pretty simple little equation there. So over at 2, that's somewhere where x is 2, this thing's vertex is going to be. And how do you know where it is vertically? Well, you look on the end and see if there was a shift. The -4 on the end, of course, shifts things down by 4. So 1, 2, 3, 4. Finally, that's where my vertex is going to be. And since we already kind of figured out the shape, it opens down and to the left. So do the reflections, it looks kind of like this. Different kind of shape for us today. Of course, we need to do domain and range, which is pretty darn easy because you have a visual to go off of. Domain is all the x's, so looks like everything from -infinity until 2, right? So -infinity to 2. And the range is all the y's, of course. So bottom to top, it does go all the way down to -infinity, but it only goes up to here at -4. So -infinity, worst infinity ever. -infinity up to and including -4. Make sure you got brackets on the ones that have to do with that point, because that point is included. It's a closed-in circle, so we're good on that. Any questions over the logic? All right, let's move right along. Number 2 today, write that one down. 2 is a 5th root. So that's an odd root. So a different kind of beast, but very similar in the same way as. So there's number 2, the 5th root of -x plus 7. And then outside the root's a -1. So yes, it's an odd root. So your mind should think of this shape right here. Do you see any negatives that might reflect things? I do. I see a negative for my x, right? And we all know that negatives with the x's reflect things horizontally. So there is going to be a horizontal reflection where this shape is kind of flipped over. If you flip this whole thing over, would you kind of buy that it looks like this now? So I think this one's going to look kind of like that-ish, kind of like a backwards one where that's flipped over there and that flipped over there. All right, we got the shape down. Now the easy stuff. Where's the center? Well, the center for this one is when the inside is equal to 0. And it wouldn't take more than half a second to figure out that happens when x is 7. -7 plus 7 is 0. So way over at 7, 1, 2, 3, 4, 5, 6, 7. And there's also a -1 on the end. That moves things down by 1. So right there. The coordinate 7, -1. That's where the center of this thing will kind of be. And again, it kind of looked like this thing creeping down a little bit. So I'm going to try to draw it the best I can. Kind of comes down, goes through there like a reflected root right there. So there it is. Your art doesn't need to be perfect. As long as you're kind of got the right shape in general and you've moved the centers of the vertex to the right spot, you are good. And that's it for that one. Number 3 ain't so bad either. Oh, good point. Got me on that one. What is the domain and range? That is very good. Absolutely. Good job on that. Yes. Both of them are the same. Any odd root at all will go everywhere to left and right, and all the way to the top and bottom. Good catch on that. You guys are going to keep me on my toes today. I like that. And then one last warm up, number 3. It says f of x is the quantity x minus 2, and that's raised to a fraction. Huh? What's a 1/8 power mean, everybody? 8th root. Yep. So this is equivalent, of course, to the 8th root of x minus 2 plus 9. You don't need to rewrite it like that. In fact, as you get older, I kind of prefer you don't write root symbols anymore. I'd rather you write 1/8 power than 8th root over and over again, but that's for the future. All right, even root. So it kind of looks like this. I don't see a negative in front. I don't see a negative from my x, right? So it's going to look exactly like that, no reflections. And would you buy that the vertex will be at 2, 9? Because 2 makes that 0, right? And that moves it up 9. So 2 over, 9 up. There will be my vertex. No stretches or shifts or anything weird. So it's just going to open up in the normal fashion. 2 over, 9 up. 2, 9. And then just looking at it, the domain clearly is from 2 to infinity. And the range is from 9 up to infinity. And we're done. So that was all that you need to know about graphing roots. You got that all figured out. You're in good shape. And today we're going to talk one more time about simplifying roots. And then you'll know everything there is to know about simplifying any root, square roots, cube roots. How do you add them? How do you multiply them? How do you get the woods? A lot of good stuff today. But that unfortunately means it's going to be a little challenging. So your goal is probably to understand, I don't know, 75% of everything today at least. There's a couple gaps along the way. I wouldn't freak out. First hour, I went a little long on this. I'm going to try and go a little faster so we can get through it. Might skip an example here and there, but if you got any questions, let me know. This sure has a lot of things in the learning goal. This section wants you to learn how to simplify roots. We've already kind of done that one. So it'll start off as a review. It's going to be like, why are we doing this again? But then we're going to talk about how you can add, subtract them, and multiply them, and divide them, and rationalize things. It's just going to be a whole big day. Woohoo! And as always, once you got that copied down, get ready to copy down the homework. New lesson, new homework. And new lesson with new homework usually means the old one's due. And it is. So please turn in homework 6.4 sometime today, either on paper or online. Either one's acceptable. Logically speaking, the next one would be called homework 6.5. And it is. So here is what homework 6.5 is. It's page 339. And 3 through 45, just the multiples of 3. So, you know, 3, 6, 9, 12, blah, blah, blah. Due Tuesday. Tomorrow will be a work day. We're off school on Monday. And when you come back on Tuesday, you should have it all squared away and done. Yes, sir.
You think we'll be at school Friday?
I have no idea. I would assume. I don't think we're going to have a snow day tonight, right? I think it's a long shot, so. Mm-hmm.
We might have one Tuesday.
We might have one. I think it's more likely to have one Tuesday. I don't know. Is it supposed to be really bad this weekend? I don't even know. Sunday to Monday? Okay. Good to know. Good to know. My girlfriend wants to know. Okay, here we go. 6.5. Here we go. Notes. 6.5's title is Operations with Radical Expressions. So this is the leftover stuff that you haven't learned yet about roots, simplifying them and working with them and things like that. And we're going to start with something you actually do know. So the first things first, I would like you to write down this rule right here in the middle, and then the key concept under the words that equation. The nth root of AB is equal to the nth root of A times the nth root of B. We've already been using that one. If you have a root and things are multiplied together, you can break it apart, correct? So if I said square root of 50, I can break that up into a square root of 25 and a square root of 2, because 2 times 25 is 50. I've already been prepping you for that all year. So that one should not be something that blows your mind right there, because we've already been doing it. I do want you to think that you can go the other way, though. If you have two roots multiplied together, like an nth root of A times an nth root of B, you can put them back together into a single root with an nth root of the product. I would like you to write down the one in the second key concept as well, because that one's new. And you might not think of that one, but you can do it for division also. In fact, you should know that multiplication and division are really the same thing in disguise. So whenever I give you a rule about multiplication, there's the same exact rule for division. And this is no different. So if you have an nth root of a fraction, A over B, you can do the root of the top separately and the root of the bottom separately. And vice versa, you can go the other way too. If you have a root over a root, you can put them together into a root of just a single fraction. So you can go either way in these two things. Definitely that one right there. And this one down here. And they got some examples for you. You can kind of check them out real quick. Like this one, 12 times 3 is 36. So you can either call it square root of 36, or you can break it up into square root of 12 and a square root of 3. Same kind of thing down here with division. If you have a square root of something on top and bottom, you can do the square root of the top and the bottom separately. That's the key things for these. Okay, let's just dive in and start looking at some examples. And I'm going to kind of breeze through these ones pretty quick, because these ones to start off are very much a review of things you've already learned before. So let's do A. We'll do A, and then we'll just kind of move on to the next topic. This is not asking you to do anything you haven't done before. We're simplifying roots, cube roots of negative 27, a to the 6th, and b to the 14th. And I've already been prepping you this for you the whole way through. You already know how to simplify roots. We've been talking about it a long time. For this one in particular, if you're looking for a cube root, well, you want to find things that are cubed, correct, that go into it. So we're going to go one thing at a time and see what we can do. Well, let's see. A negative sign, that's interesting. Did you know a negative times a negative times a negative is a negative? Okay. So I could call this negative a negative 1 cubed. It's weird. Good. Because a negative times itself, an odd number of times is always a negative. What about 27? Is that something cubed? Anybody got that list out? You might want to get that table out too. 3 is 3 cubed, yeah. It's funny how you start to memorize them after a few problems, right? Like you see the same numbers, 27, 81, etc. Good, very good. Okay, how about the a to the 6th? Remember what the trick is? You take the exponent divided by the root, correct? So this does work out. 6 divided by 3 is clean. It's 2. So I can think of the a to the 6th as an a squared cubed. And this last one, b to the 14th. Now this doesn't work out, does it? 14 divided by 3 is not pretty, correct? But 12 divided by 3 is, right? So what you're going to do is you're going to break the b's up into a 12 and a 2 with a leftover. And the reason you're going to do that on the next line is, well, 12 divided by 3 is pretty. It's 4, correct? So you can call the b the 12th, b to the 4th cubed. And that's why you're doing that. That way you can write it as something cubed. I do see a leftover. What's the leftover going to be? B squared, right? And that's really the one thing that they're saying right here is, since these are all multiplied together, you can do them all separately, but we've already been doing that all year long, so this really shouldn't be a surprise to you. Now here I got a cube of a cube root, so they cancel, correct? And you're left with a negative 1. I'll just write negative because it's going to be times something else. The cube root with the 3 cubed cancel, you have a 3. The cubed root with the a squared cubed cancels and give you a squared. And same with the b to the 4th. Those are all the ones that were perfect cubes. So those cube roots will take care of it. And no need for an absolute value on this because there's an odd root But there was something left, wasn't there? So just like we've been practicing, if there's a leftover, it just chills inside the root. You can't really do anything with that. And that shouldn't be anything new. We've been doing that already, correct? Now, one thing I would like you to note about this, and you might want to write down, if you have an odd root of a negative, look what happened to the negative. Basically, it just came out to your final answer. If you have a negative under an odd root, you can just bring it out. That's good to know. Odd root of a negative is always a negative, every single time. So if I had 7th root of negative something, it'd be a negative something. If I had 21st root of negative something, it'd be negative something. And that's pretty much all there is to that. Let's do one which actually has some division in it, though, because that is new to us, although it's very, very similar. So it's nothing to freak out about. Don't let the fact that there's a fraction scare you. It's going to be the same thing. Let's take a second to write that problem down. Cubic root 24 and 6. All right, so really the point of this problem is, if you can break things apart with multiplication, you can also break them apart with division. So we can do the top and the bottom separately. That's kind of what this whole point is. So the top, I'll just take the cube root of that separately. And on the bottom, I'll take the cube root of that as well. That's our new property. You can do this for division. And beyond that, it's really just doing 2 problems in one. I got some stuff on top. I got some stuff on bottom. We're going to simplify them both and see what happens. On the top, I'm looking for cubes that go into 24. You got a list of your cubes right there on your chart somewhere? Hunt for a cube that might go into 24. 4 is not a cube. 8. Okay, I'm down with that. 8's something cubed. 8 is 2 cubed, correct? So I can call the 24 an 8 times a 3. So I'm going to write 8 times 3, but I know I'm doing that because 8 is 2 cubed. Well, that's good. And similarly, this 8 to the 6th, well, it's something cubed. Again, use your little trick. 6 divided by 3 is 2, correct? So I can think of that as a squared cubed there. And down at the bottom, well, I got a 125. But if you look on your cubes, that's something cubed. That's 5 cubed. So we're just going to clean this up and see what happens, just like always. 2 problems in one. On the top, the cube root and the 2 to the cube cancel, and you just have a 2. The cube root and the a squared cube, the cubes cancel, and you're left with an a squared. So we took care of the pretty ones. And that 3 is just left over, unfortunately. So we have a cubic root of 3 still chilling on top. And then down the bottom, got a cubic root of 5 cubed, so that's just 5. And we're done. And that's not that tricky. You're just doing the same thing on the top and the bottom. Just know you can split apart like that. That's really all there is to it. That's the same idea. Let's practice one on your own. Write this down and try it. You try it. Give it a shot. Here it is. It's a big check thing. Boom, boom. Write the simplified form of this. And then I'll put it on the board in a second, and we'll check and see if we got the same thing. You are doing a square root and even root, so do be aware that you might need some absolute values. I keep doing that. Whole points like that. You can take the root and put it on the top and the bottom separately anytime you want. At any stage, you're allowed to do that thing. And I hope the first thing you started doing was looking for perfect squares that go into things. Is that what we were doing? So on the top, I'm seeing a 9. That's 3 squared, right? I'm seeing a y x to the 8th. Now, that divides by 2 evenly, doesn't it? So I can call that x to the 4th squared. Now, I ran into a bit of a problem with the y to the 13th because 13 doesn't divide by 2 very evenly, does it? But 12 does. So I broke it into a 12 and a 1 y and 12 y's. And the y to the 12th could be thought of as y to the 6th squared times a y. And down the bottom, it's pretty straightforward. 25 is 5 squared, and x squared is obviously x squared. So I broke the root up into 2 parts, and we're going to clean them up separately, and we're going to see what happens. So did you get this? Let's see. The square root of 3 squared is 3, correct? Square root of x to the 4th is x to the 4th. Do you need an absolute value on that one? The answer is no, because it's raised to an even power, and things raised to an even are always positive. Same with the y to the 6th. But unfortunately, there was this leftover y, so we have a leftover y left in a root. That sucks. Down on the bottom, well, the square root of 5 squared is 5. And the square root of x squared, they cancel, but absolute value, because x could, in fact, be negative. So there's your final answer. If you got that far, it's pretty darn good. You got started on it, and maybe you got stuck. Take a look and make sure you understand why you got stuck, and then that's all there is to it. Questions over any of this junk from anybody? That's not so bad with division, I don't think. Now, the next topic is adding and subtracting these things, and there really isn't much to say about this. There is no formal notes. Here's my, let's just look at an example because you got to see it done. Write this example down. If there is one note for you, it would be to simplify every root by itself and hope they have a like term in common so you can add and subtract things. So I don't really, there's nothing new to this. Just simplify each root separately. There is no rule for adding and subtracting roots together unless they're the exact same roots. So this one starts off with, what's that? And hopefully they have something in common. For example, this one right here, if you look at the things involved, the first one has a 45x under a root, right? Is there a 45x under any other root? Nope. This is not the same as this. It's not the same as this. They're not like terms. And if they're not like terms, there's no way to add and subtract them. So you might think, oh, I'm just kind of stuck on this. Well, how can I add 6 of these things and 3 of these things if they're not the same things? You can't. But if you have faith and you simplify these roots, maybe they will have secretly something in common so you can add them together. And that's the whole strategy. So we're just going to do them one time. Here we go. This root, let's try to simplify it. 45. Any squares that go into 45? Nine. Yeah. 9 is 3 squared, correct? And 9 times 5 is 45. And there's still an x under there, too. Can't do much with the x, right? All right. Shoot. Well, let's move on to the next dude. How about 12? Any perfect squares that go into 12? 4 does, yeah. 4 is 2 squared, and 4 times 3 is 12, so that's good. And we just keep doing it for every single one. We're not doing anything special. Got roots. We're simplifying them. How about 20? I think 4 goes in that too, don't you think? So let's call it 4, 2 squared, times 5. Do you see how they do kind of have something in common now? This is going to simplify, isn't it? And what's going to be left over? A 5x under the root, right? And this one's going to simplify, and it's going to have a 5x. These will end up being like terms that I can add together finally after I do this. Well, let's simplify first. First of all, the square root of 3 squared is just 3, right? And 3 times 6 is 18. So this turns into an 18, and the 5x is still left under the root because it wasn't pretty, so we're stuck with it. Similarly, for this one, the 2 squared and their square root are going to cancel, so that'll just leave me with a 2. But there's that 3 left over we couldn't do anything with, so we have an awkward square root of 3 left. No need for absolute values on these because we're just getting out 2s and 5s and stuff like that, and those are already positive. And this one right here, same deal. The square root of the 2 squared will cancel, giving me a 2. But next to a 3, 3 times 2 is 6, right? And you still have this awkward 5x under the root. But now you see there are definitely like terms involved here. This thing is the same as that thing. So I can compare, I can add apples to apples. 18 things minus 6 things is 12 things, right? So those two are like terms. Unfortunately, this one in the middle is not like. Would you agree? 3 is not the same as 5x. I can't really add those. That's apples and oranges, so they're just kind of stuck separated like that. But that's the point of how you add or subtract roots. You simplify them separately and hope that they have something in common that you can add or subtract together. Does that make sense? Eh? Say words. Yeah, all right, I like that. That's good. All right, let's see if you guys can do one. That one at the bottom of the screen. Take a second, you try it. See if you got this. Just do each root one at a time. And I'll even give you some hints on the board, so you don't have to look at your table. I'll tell you what goes into 18, that's a perfect square. I'll tell you what goes into 28, that's a perfect square. I'll even tell you what goes into 98, that's a perfect square. I'll just save you the time of hunting. If you're getting real good at these, you can start skipping steps. I wouldn't advise it. The more steps we skip, usually the more off the rails it goes. All right, let's at least talk about what you should have got going theoretically. First off, 18 is 9 times 2, right? And the square root of 9 is pretty. Square root of 9 is just 3, right? So there's a 3 that comes out, and what's left over is the 2, so you have a 2x left under your root, right? Too much too fast, or we got on 2 steps at 1? This one right here, same story, 28. 28 is 4 times 7. Well, the square root of 4 is 2, right? So I have a 5 times a 2, which is a 10. And I have this 7 left over, so it's a square root of 7. And so on and so forth down the line. 98 is 49 times 2. The square root of 49 is 7. And 7 times 3 is 21. Oh, why is there a 7 left? That should be a what? That should be a 2. I'm an idiot. And then that one over there, there's really nothing you can do with 7. Would you agree? Yeah, 7, nothing goes into that, so we're kind of done. Okay, are there like terms we can put together? I only see 2. Do you see 2 things that are the exact same thing? This has a root 2x, right? And that's a root 2x. Are these like terms? No, that's a 7 and that's a 7x. So the only thing we can do is put these two together. And 3 somethings minus 21 somethings is negative 18 somethings. In our case, square root of 2x. And there's really nothing else we can do with this other leftover stuff. So if you got all the way to there, fantastic. That's awesome. But there's just one more time to model it for you. I think you guys get the gist of adding and subtracting. You just got to do them separately, right? And see what the heck they do when they put them together. Okay, so for the sake of time, we're going to keep on moving on. We do need to, there's one more we should look at, though. This is one you haven't done before, so let's do this one. Write down this top line. It's going to suck. Won't take that long, though. We'll be okay. This is a different flavor, a different strategy. Now, this one, let's just look at it fresh. Forget what they're doing. Let's just look at what we're doing. Fifth roots. Well, if I look at this guy, I don't think anything to the fifth power goes to 10. Would you agree? And 2 divided by 5 isn't pretty, is it? And 6 divided by 5, well, I could break that up into a 5 and a 1, but that doesn't simplify it too much. Would you agree? This one, nothing to the fifth power goes into 16, and 4 doesn't divide by 5 either, does it? So it seems like there's really not much you can do. Well, here's the sneaky thing you're going to do. If you have a problem like this, where you have something times something, you don't think it's going to clean up much, put them back together. You know, we can take roots and split them apart. We'll put them back together. So that's exactly what we're going to do on this particular problem. Now, unrelated to the roots, what do you got? A 4 times a 3? So that's just 12. So I got a 12. I'm done with that 4 and that 3 to hell with that. The rest of the stuff are in under fifth roots. So like I just said, we're not going to break them apart. We're going to put these back together. So all this stuff in the first root times all this stuff in the second root. We're getting desperate. It's like a desperate move. You know, if you can't find anything to simplify, try shoving them back together into one. And then clean up what's inside. Let's see what this stuff is inside when we put this all stuff back together. Well, you got a negative 10 times 16. That's obviously negative 160. What do you got? An x to the 6th? Would you agree? Put those together. X to the 6th. And a y to the 10th. So I'm just looking at it in a new way. How about this thing? Well, you know, nothing up here had anything to the fifth power that really went into it very nice. But maybe now there's something that goes to the fifth power in this. 160. Get out your things raised to the fifth power chart and tell me if any number goes into 160. I believe one of them does. And if you're not sure, go start taking 160 divided by one of them and divide by another one until you can find it. Or I'll just tell you. There's a 32 on there, isn't there? Yeah. It turns out 32 does go into 160. If you don't know that, you got to start guessing, right? 160 divided by 32. Oh, it's 5. Okay, that one works. So we're going to write the 160 as a 32 times a 5. Because 32 is 2 to the 5th. So that's fine, too. The x to the 6th one, well, 6 divided by 5 isn't pretty. But I can break that up, too, can't I? X to the 5th and an x to the 1st. So I'll break it up into an x to the 5th and an x to the 1st. That x to the 1st is going to be the leftover jerk. And the y to the 10th, well, that's going to work out nice because 10 divided by 5 is just 2. So I could right now just think of that as a y squared to the 5th power. That's awesome. Now, if you look at it this way, do you see the benefit of maybe going down this route? Up here, I had maybe one thing that would simplify, you know, because 6 divided by 5, I could make that something. Down here, how many things are raised to the 5th power now? 1, 2, 3. There's a lot of simplifying that can be done now. So putting them together sometimes helps you out. As mentioned earlier in the lesson, if you have an odd root of a negative, It's just a negative, so there's going to be a negative 12. Let's see what else we can take care of. Took care of the negative. Well, the fifth root of 2 to the fifth is just 2, right? That's done. That's done. The fifth root of x to the fifth is just x. And the fifth root of y squared to the fifth is just y squared. And there is some leftovers. There's a 5 and an x that really had nobody to hang out with. So they're going to be little loner losers like me on a Friday night. Fifth root of 5x is all that's left. And we're done with that one. Okay, so you're seeing lots of different ways they're going about this, but keep that one strategy in mind. You might want to put them back together and see if something simplifies. All right, last topic of the day. Here we go. This one is called Rationalizing the Denominator. Please write down the title of Rationalizing the Denominator, because that's what it's called. In a fancy way, that fancy term is just saying what's in that box right there. When they say to rationalize the denominator, what they're really saying is, I want you to find a way to make so there's no roots in the bottom of your fraction. You can't be dividing by square root of 6. You can't be dividing by fifth root of 8. You can't be dividing by roots. Honestly, it's not a too useful skill. It's more left over from historical reasons back in the day when dividing by, you had to do it with your brain instead of typing it in. That's you. But it is still useful. So when I say rationalize the denominator, what I'm really saying is make the denominator pretty. No roots in it, no nothing. They give you a cute little template of how to do that. And I probably would write it down, I guess. I'll try to teach you to do it instinctively, but here's this table. If the denominator has a square root in it, the method to get rid of the square root on the bottom is to multiply the top and bottom by that exact same square root. So if the bottom has a square root of b, then you multiply the top and bottom by square root of b. The bottom has a square root of 9. That's a bad example because that's 3. But the bottom has a square root of 17. Then I multiply the top and bottom by the square root of 17. Most of the time in your life, you're going to be cleaning up square roots. That's a pretty easy thing to do. But once in a while, you do have like a weird root on the bottom, like a cube root or a seventh root or something. And that's what that second line in your table is for. If you have an nth root of b raised to some power, it doesn't work out clean, then you can multiply by that thing in the middle, the nth root of b to the n minus x, which seems kind of weird. And I'll try to explain to you instinctively why that works later on. And it'll turn out pretty now. Beyond those two things, I would like you to write down the word in bold down there. Conjugate, it's back. We've already talked about the term conjugate before. When we did, we applied it to complex numbers. Remember what a complex number conjugate is? It's the same exact thing with the sign change, right? If I gave you 4 plus 5i, and I said, what's the conjugate? You'd say 4 minus 5i. Well, this conjugate thing is good for more than just imaginary stuff. It's good for roots, too. So if I give you a root. Yes, ma'am.
You notice how it says the 4 over the square root of 7?
Yes.
How is it equal negative 4?
They got a negative sign there?
See what I'm saying?
I do see what you're saying. There shouldn't be a negative sign there. That doesn't make any sense. I agree. Yeah, that's I don't know why that's there. Yeah, don't write that negative sign. That makes no sense. Like right here, they got a negative in front of it. Just came out of nowhere. You know what I think they're doing? You know what I think is happening is this is the division bar, and then this graphic they're putting down below here is kind of cutting it off a little bit, so it makes it look like a negative sign. That one's actually okay. That one's actually okay. There's no negatives over here. I don't know what they're talking about. That's stupid. Wow. Good catch. I didn't even notice that. Conjugates, though, are kind of what you think they'd be. And it can be anything. Okay, so before we dive into some problems I actually do that, make sure it's very clear on what this conjugate thing means, because that will come up at the very end. And here's the example again. If you have something plus something, then something minus it is the conjugate. It can be the most complicated thing in the world with roots that you can't add or subtract, but the conjugate just means you change the sign in the middle, right? You start with a negative one, you make it positive. And that's really all there is to these kind of things. Now, how the heck does this work? I do want you to look at this slide real quick, okay? This kind of says the whole picture. If you start with 4 over square root of 7, why might you multiply the top and bottom by a square root of 7? What happens on the bottom? What's square root of 7 times square root of 7? It's just 7. That's why that works out. Now the bottom has no weird roots, and that's the point. It comes at a cost. The top has a weird root now, but the point is to rationalize the denominator, the bottom. We want the bottom to be pretty right here. Now here's another one. Now, this is the weird one, so I really want you to pay attention on this one. Down here, they have a 5th root of 2, correct? The only way that this could not have a 5th root is if you had a 2 raised to the, what power? 5th. But you don't have a 2 to the 5th, do you? You just have a little 2, right? How many more 2's would you need down there if you wanted 2 to the 5th? You already got 1, you need 4 more. So that's why they choose to multiply by the 2 to the 4th on top and bottom right there. Because then when you put them together on the bottom, there's 4 from this one, there's 1 from this one. That's a grand total of 5 of them. And that's the main thing that this complicated thing is here is saying. If you got a 5th root, you need a total of 5 2's on the bottom to make it work. If you only got 1, you got to put 4 more. And the conjugate thing we'll talk about too in a minute. Okay, so let's do our very first example here. Example number 6, jot this down. And we're going to just do this one and maybe one more and call it a day. Bell to bell today. Cubic root. 250, 8 to the 6th, 7a. All right. So building on the skills from earlier in the lesson, I have something divided by something. I'm not going to freak out. I'm going to do it separately. Let's try to do the root on top. And we'll separately do the root on the bottom. Okay. On the top, well, 250. I get out my list of cubes, and one of them is 125, which does go into 250. And 125 goes into 250 2 times, but I can write 125 as 5 cubed if you look up your table. So that's the same thing as 250. 5 cubed, 125 times 2. And the a's are going to work out nice and clean because 6 divides by 3 nicely. I could call the a to the 6th an a squared cubed. That would be great. Down on the bottom, I really don't think there's anything we could do. There's no cubes that go into 7. A is not a cube, so we're kind of stuck with that one. There's not much we can do. That's lame. On the top, the cube root and the 5 cubed, the cubes cancel. We have a 5. That dude's done. We got a cubed root of a squared cubed. So those cubes kind of cancel. We have an a squared. And there was a jerk left over. There's a 2 left over. So there's a cube root of 2 still chilling up there. And like we said, we really can't do anything with the bottom. Now, nothing up to this point is about rationalizing the denominator. Everything we've done so far is just the same thing we did in the other examples. We got some fractions. We're breaking them into parts. We're breaking them down. Here's where the rationalizing comes into play. Rationalizing is a fancy way of saying I don't want weird stuff on the bottom. Now, follow the logic very closely on this. This is a cube root, correct? So I need the stuff in here to be cubed, right? I need 3 of these things. I need 3 7's and 3 a's. Would you agree? That'd be great. Well, I only got 1 of them, don't I? So how many more do I need? I need 2 more. So you literally will multiply the bottom by 2 more 7's and 2 more a's. That's the logic. Don't go to that stupid formula in that table. I mean, you can if you need to. But just remember, you're trying to get to be things raised to that power so they cancel out. But like any fraction, you can't just multiply the bottom by something. You also have to do it to the top. This usually comes with a cost. The top gets grosser, but the bottom gets prettier, which is the point. Where? Here? That's a 3. They're all cube roots. The entire problem is cube roots everywhere. And let's see what we do have up top now. Well, let's see. Well, that's there, right? Now, these two are the same kind of root, correct? Nothing cancels on the top because these are squares, right? We got cubes. So really, I'm left over with this and this. And I don't like 2 separate leftovers. So just so I don't have 2 leftovers, I'm going to put them back together into 1. And what could I call everything on here? Well, I got a 2 times a 7 squared. You could write 2 times 7 squared, or I'll just turn to a number. 7 squared is 49. 49 times 2 is 98. And you also had an a squared left under there. Almost done. One more thing. Here's the magic. Down here, if you multiply these all together, how many 7s are there all together? There's 3. How many a's are there? 3. So the cube root's going to cancel with all those and just leave you with a 7a, which is the bloody point of rationalizing the denominator. That's plenty for today. Start on your homework, and we will talk more tomorrow. The warm-up will probably include an example with conjugates because we did not get to that, but that's okay.
Okay.